So far we've been looking mostly at phenomena. Now we would like to discuss phenomena, but we would like to closer towards materials and devices. This was my promise before the midterm. So now we're going to start looking at magnetic structures. Magnetically ordered structures. And what kind of role do the different interactions, such as the dipolar interaction, the exchange interaction, the spin orbit interaction, and the Zeeman interaction plays in determining the properties of different kinds of structures. But first of all, we would like to give a survey of what are the different structures, different kinds of structures. First of all, we have the ferromagnetic structures or ferromagnetic materials, which I may denote as Fm. In a ferromagnetic material, a solid, for example, we may have a lattice, and one kind of ferromagnetic material can have spins or angular momentums that are localized on points of the lattice, and all of these spins are pointing in the same direction. These are localized spins. Remember, we've discussed localized spins in detail, and we've also looked at accident electrons, magnetism due to delocalized or free electrons. Now, for the time being, this kind of ordering in which the spins are localized on different lattice points and all of those spins are pointing in the same direction represents ferromagnetic ordering. Now, why does this ordering come about? Even before the advent of the Heisenberg's exchange interaction, there was a model proposed that described this kind of ordering. That was due to Weiss in 1906. We're going to study that model today. No, it's due to the exchange interaction. We'll study why does this kind of ordering appear. Yes, it's possible. So you have rare earth ions or transition metal ions in an insulator. You have a paramagnetic material. In certain cases, you have ferromagnetic ordering, and this ordering is long range. It extends over the entire crystal, for example. Generally, this kind of ordering extends over regions inside the crystal which are called domains. Okay? And Weiss's theory also explains why do domains exist. So this kind of ordering is ferromagnetic ordering, and today our task that we are beset with is why does this ordering occur? Remember that when in our common everyday language when we say a magnetic material, it's generally a ferromagnet, like iron, nickel, cobalt, or one of those ferrimagnets like iron oxide. So this is ferromagnetic ordering. There could be another kind of ordering which is called antiferromagnetic ordering, AFM or AF. In antiferromagnetic ordering, what we have is a situation which is quite puzzling. We have lattice points, and on each alternate lattice point, in either direction, in this 2D as well as in the 3D, so you missed one lattice point, so all of the spins on these lattice points where you missed one intervening point, these spins are pointing in the same direction, whereas adjacent spins so here Let me first complete this diagram and then I'm going to explain what's happening here. So in this kind of ordering, we have spins on adjacent lattice points that are in opposite direction, that are anti-aligned. So this spin is anti-aligned with this spin. This pattern appears in this dimension as well as in this dimension as well as in the third dimension. So this kind of ordering in which neighboring spins are anti-aligned and the order persists throughout the domain perhaps is called antiferromagnetic ordering. So one way to look at this is this lattice could be decomposed as two sub-lattices. One is a lattice A and the other is a lattice B. Each lattice is ferromagnetically ordered within itself, but the two lattices have antiferromagnetic coupling amongst themselves. So this antiferromagnetic state can be written as a superposition of two ferromagnetically ordered states in which the two lattices are ferromagnetically coupled with respect to one another. So this is antiferromagnetic ordering. In antiferromagnetic ordering, the moments on side A and the moments on side B, they are the same in magnitude, opposite in directions. So as a whole, this domain is going to be unmagnetized. The magnetization is 0 if it's a perfect antiferromagnet. So if you have a magnetization here M plus, you have a magnetization here M minus, the overall magnetization is M plus minus M minus, where these are the magnitudes. Yes? क्या चीज इसको ऐसे कैसे लिखें? So just visualize, this is, you can decompose this lattice into two lattices. One, you can take sides, so let's call these sides A. All of these are sides A. Okay? So this lattice is lattice A, and then you have sides B, the lattice B. This is side B. So A is, the sides on A are ferromagnetically ordered, the sides on B are ferromagnetically ordered, but they're antiferromagnetically coupled with respect to one another. For example, Fe3O4. In Fe3O4, there are two kinds of iron ions. So when we're going to study these structures from a crystallography point of view, but there are two kinds of ions. One group is on a tetrahedral sites, and the other group is on octahedral sites. So this forms one lattice, this forms another group of iron ions. And they're antiferromagnetically coupled with respect to one another. But all octahedrally placed ions are going to be ferromagnetically coupled with respect to one another. This is an example of what is called a spinel structure. We're going to look at this in subsequent lectures. So this is antiferromagnetic coupling. You could also have ferrimagnetic coupling.
This might be a minor point, but in the both the domains which are coupled together antiferromagnetically.
They are not domains, they are two different interpenetrating lattices. Domain is a particular word.
So these two lattices, so here the density of the final lattice will be different from the two constituent lattices.
Right.
It has different number of moments per unit volume.
Right. But if you look at this, this is in two dimensions. This forms one unit cell in the magnetic domain. Okay? This is one unit cell in the magnetic domain which comprises A and sites on A and B. This is one unit cell, and the entire structure can be built up from these unit cells. Chemically, the unit cell is this one. The chemical unit cell is this large, but the magnetic unit cell is only this large. So the magnetic unit cell does not coincide with the chemical unit cell.
And so what about the unit cell of this structure?
This structure? Which unit cell? Magnetic or chemical?
So magnetic.
This is the magnetic unit cell, and this is the chemical unit cell. Okay. Now in antiferromagnetic ordering, so we've looked at ferromagnetic ordering, antiferromagnetic ordering. In ferrimagnetic ordering, what happens is that M plus is not the same as M minus. So you have A and B lattice sites, and the two magnetizations don't cancel out one another. So the net magnetization, which is M plus minus M minus, is not equal to 0. In fact, you can get large magnetizations in ferrimagnetic materials. So the common examples of ferromagnetic materials, if we talk about elements, they are nickel, cobalt, iron, gadolinium, dysprosium. These are the 5 elements that are ferromagnetic at roughly room temperature. This has a Curie point near room temperature. Examples of antiferromagnets are manganese oxide, chromium oxide. Okay? An example, the most important example of ferrimagnets is given by Fe3O4. Iron oxide, FeO, is antiferromagnetic. Then you will have a large number of rare earth compounds like neodymium, iron, boron, samarium, cobalt. The list goes on and on for ferromagnets. And all of these materials, especially the ferromagnetic and the ferrimagnets, are commonly called magnetic materials in our everyday language. And they're important because our entire civilization depends upon, especially the production of electricity, the distribution of electricity depends upon transformers. It all depends upon, it's all an interplay of ferrimagnetism and ferromagnetism. Okay? Without this technology, life will not exist as it exists today. Okay? So we have ferrimagnetic materials, ferrimagnetic ordering. We can have other interesting kinds of ordering as well. For example, we could have another kind of ordering in which you have lattice sites and there are spins on each lattice site and they're pointing in random directions, just like an amorphous material crystallographically. But these spins are frozen in time. Generally, if you would make such a material, it's called a glass. So how do you make a glass? You have a liquid and you cool it suddenly. So you have a liquid in which the atoms are moving about in random directions. You cool it suddenly by the process of quenching. You cool it suddenly, and the atoms, wherever they are, they remain frozen in their respective locations. Likewise, this kind of material is called a spin glass. This is spin glassy ordering, in which the different spins are pointing in random directions, but they're frozen. They're not at 0 Kelvin. This will be the orientation of these spins. This is called a spin glass. It's a kind of magnetic analog to an insulator. to a glass. It's a magnetic analog to a glass. And these are formed by rapid cooling of disordered materials, magnetically disordered materials. You rapidly cool them, the spins get aligned in random directions. Of course, the overall magnetization in this domain is also going to be zero if this is a large enough sample. So this is a spin glass. Then you may have other kinds of ordering. For example, you may have what is called spherical magnetism or helical magnetism. In a helical magnetism, if I draw a line here and I draw a circle which is concentric with the line, and if the spins are at different positions, they have their spins pointing along the perimeter of these circles, so that one forms a helix. If you connect these points, one forms a helix and it goes on. This is called a helical magnet. This is helically magnetically ordered sample, or helimagnetism. Okay? And this is a very popular form of magnetism for rare earth materials. Likewise, you can also draw cones here. And if the spins lie on surfaces of these cones, and so on. And once again, you have a helical kind of structure. But now the arrows of these arrows, which are the spins, they lie on the surface of a cone. And this kind of magnetism is called conical magnetism. So there are different kinds of magnetic ordering that can exist. Now what we would like to do today is we would like to discuss how do we explain this ordering and what is the origin of this ordering. First of all, remember that the order that we are discussing is a long range order. And this order is seen at room temperatures. So we know that the thermal energy at room temperature is about 25 milli-electron volt. So we must have an energy advantage in forming ferromagnetically ordered states at this temperature, which means that the energies that are associated with this kind of ordering must be at least of this magnitude if you would like to see room temperature order. And of course we have room temperature ferromagnets. And we also know it's a long range effect. So one of the interactions, the dipolar interaction, does not qualify, is not able to generate this long range order at high temperatures. Because of what reasons? What are the reasons why the dipolar effect falls short? Because it's small range. First of all, it's small range. It depends upon 1 over r cubed. And it falls off on the order of nanometers. But these are macroscopic domains. The size could be of the order of microns to millimeters. So, number two, the dipolar interaction is really, really small. And we've already seen that it's about the dipolar interaction of two dipoles that are close together and they're separated by, say, 1 nanometer would be 2 to 3 times smaller than this. So the dipolar interaction cannot explain this kind of ordering. So what can? We'll see that the exchange interaction can explain this ordering inside the solid. Okay? But before we look at exchange interaction, we would like to come up with a popular description of this kind of magnetic ordering, and we would like to use a mean field theory. Now these mean field theories are extremely popular in statistical mechanics. And one mean field theory which describes this magnetism is Weiss's magnetic field theory, which was proposed around 1906, before the advent of Heisenberg's mechanics and before most of quantum mechanics was ever built. Now, it's a successful theory, it's a good model that describes this kind of behavior. Now what we would like to do is we would like to study this Weiss's molecular theory. All right. Yes.
So the question that I have might be a good example of jumping the gun and all sorts of expressions for asking bigger questions at a very small scale. So I understand that magnetism is a vast topic and hence we are just surveying broadly the field. But so the overall trend has been that it's more of an empirical study up till now, as in we have a model, we have certain phenomena that need to be described, and hence we try our best in understanding the basic concepts that we have and trying to explain.
But all physics is like that.
It's true.
All of physics is like that.
But sir, can we, as students of having taken this course, can we develop some sort of intuition about what might be expected and what might not be expected?
Of course, the point of this course is to introduce the different phenomena, and those are all derived from basic quantum mechanics, and we've already taken that route. So now we're going to apply this to different scenarios. So it has immense predictive power. Okay, so it's all can be predicted. But when you have large systems, as Anderson said, many is different. You have a big system, it's different from a small system. So you would need to use more complicated models. You need to use density function theory, spin density function theory to be able to predict something. But of course, all of physics is like what you said. All of physics is empirical. All of it is like that.
But so it was just like we can have this sort of ordering, and so this got me thinking that if I am told that this sort of ordering can also exist, but
yes, you can prove that. You can come up with whether it is energetically favorable to have an ordering. For example, one homework problem that I might give you is, if I have a single chain, can I have antiferromagnetic ordering in that single chain? Okay, so this you can work out from first principles. Yes, you can do that, but only for simple problems. Alright, so what is Weiss's magnetic field theory? Now, first of all, I would like to give you an idea of what model did Weiss come up with. We all know that if we have a paramagnet, the magnetization of the paramagnet is given by saturation magnetization into the Brillouin function, where this Brillouin function is defined as 2j plus 1 over 2j cotangent y minus 1 over 2j cotangent, this is y over 2j, this is two j plus 1 over 2j y. Now we derive this from first principles, and if you make a plot of this function, I have y on this axis, here I put m over ms, okay, and I call this m star, which is the magnetization as a function of, as a ratio of normalized with respect to saturation magnetization. The curve that I get, I all know, looks like this, and it depends upon the value of j, the spin. Now what we are assuming in the ferromagnetic state is that each spin has an angular momentum j, some j, and all of them are localized. But that's a ferromagnet, whereas this is for a paramagnet. Okay? Now what Weiss's molecular theory states is that if I have a paramagnet, in order to achieve that kind of ordering, what do I need? I can have this kind of ordering in a paramagnet. I can have it at room temperature. But what do I need for that? Suppose I have no concept whatsoever of ferromagnets. Ferromagnets don't exist. I'm only given a paramagnetic state, and I would like to achieve that kind of ordering. What would I need to do? Where would that kind of ordering lie on this graph? That would lie at large values of y, and this y is proportional to b over t. Remember, that my y is given by x times j, and my x is given by gj mu b over kbt, right? These were our earlier lectures on isolated magnetic moments. Now if I would like to have the magnetization to be equal to the saturation magnetization, I would like to be somewhere here, I would need large values of y, which means I would really need to go to low temperatures and ultra large magnetic fields. Okay? So I need to be on this point in the graph, somewhere here, if I only had paramagnetism at my disposal. I need large magnetic fields to achieve this kind of state. But a ferromagnet can be ferromagnetically ordered even in the absence of magnetic fields, because there is this concept of spontaneous magnetization. A piece of iron, if it is magnetized, such as I can have a permanent magnet, a magnet can attract iron, other pieces of iron. So it has its spontaneous magnetization, it produces a field of its own, even in the absence of an external field. And here I am claiming that I need large magnetic fields to achieve this kind of state. And I need low temperatures according to this Brillouin function. But I have ferromagnetism at room temperatures. So how do I explain this effect? Weiss's theory actually says, okay, if I have a paramagnet and I want to achieve that kind of state, I need some internal molecular field. Some field which each spin is actually seeing. I don't know what the origin of that field is, but there is some field inside the solid, a fictitious field, which must exist inside the solid that attains this kind of ordering. Okay, that field is Weiss's molecular field. The first question we would like to see, okay, what should that field be? How large should that field be? The second question we would like to see is, what's the origin of that field if it exists at all? Right? So this is the question at hand. So the first point is that according to the Brillouin function, this is our magnetization. And I also know that my y equals this. In other words, my y equals x is gj mu b over kbt x. Now what is this b? This is an external field. Alright, this is an external field. Now what Weiss proposed is that there is some internal field as well, in addition to this. Right? In all the formulas you would agree with me that this is the field that is imposed upon the solid from the outside. So it's an external field. However, Weiss has proposed that in addition to this field, there is another field, BMF, a molecular field inside the solid, origins as yet unknown. And this is proportional to the magnetization of the sample. The higher the magnetization of the sample, higher should be this field. And there is a constant of proportionality called lambda, a molecular field constant. So this is Weiss's conjecture. Okay. Now we could replace this B with B plus BMF. Alright. So now this is our new Y. This new Y would also appear here. So now we have one scenario. One scenario is, suppose a ferromagnetically ordered material is placed inside an external field which is 0. External field B is 0, which means only BMF is equal to lambda m exists. Now remember, there is a kind of chicken egg problem here. There is an internal field due to a magnetization. due to magnetization of the material. But where is this magnetization coming from? Which means the sample has been magnetized by placing it in some external field. So, but if we ignore this chicken and egg problem, if the sample is magnetized, it will produce some internal field, and that internal field is ordering those spins, putting those spins in order. Right? So now we have two kind of equations. In one equation is the Brillouin function equation, which tells us what the paramagnetic state is. So we have m equals ms, or m over ms equals bjy. So bjy is now gj mu b. Instead of b, I write lambda m, because b is bmf kbt, and I have a j as well here, right? X, y is equal to x times j. So this is my new x. All of this is my new y. This is my y. The other equation is my y equals x, which is gj mu b lambda m over kbt into j, xj, right? Now I have two equations. One is this equation, and I can look at this equation, m equals y into kbt gj mu b lambda capital J. Now this is one equation, and this is another equation. Alright, now what I could do, now if I plot m here and y here, and I have a paramagnetic material in which there is some internal field which tries to order the spins. If I plot this equation, I get the Brillouin function. This is ms. Now if I plot this function, this is a linear function of y, and it depends upon the temperature. The slope of this straight line would depend upon the temperature. Alright? So I can get a line like this. This is 0. I can get a line like this. I can get a line like this. I can get a line like this. I can get a line like this, like this. It all depends upon the temperature. Higher temperature means higher slope. So these lines correspond to higher temperatures. Now if there is an internal field inside the solid, then that internal field must produce a magnetization which is compatible with both of these graphs at the same time. The internal field is described, the internal field results in a magnetization which is describable by the Brillouin function, and the internal field is also describable by this function. So the magnetization which is allowed would be points of intersection of this yellow graph and the green lines, which means that I have one equation which is given by this, the other equation is given by the straight lines, and these points of intersection are solutions to both of these simultaneous equations. I notice that m equals 0 is always a solution. This point is always a solution. So the sample can be unmagnetized, but it's also possible that for certain values of y, I can get solutions, I can get magnetizations. I can have an internal field which can magnetize the sample. Okay? Now, how do we explain this? How do we look at this problem? We look at this problem in the following way. If my slope is smaller than a certain critical value, then I will have non-zero solutions to the magnetization, which means that the sample can be magnetized with an internal field lambda m. If I have a slope which is larger than a critical value, then no solution exists to both of these equations. The only solution that exists is at n equals 0. So the sample is unmagnetized. So I have two regimes here. In certain temperatures, I can sustain magnetization inside the sample, even in the absence of a magnetic field. Remember, I put B equals 0, so only this is my internal field. Only an internal field exists. There is no B here. Only an internal field exists. This is the internal field, BMF. There is no external field. This is BMF. No external field, only an internal molecular field. So at certain values of y, which are solutions to these simultaneous equations, I can have a magnetization even in the absence of a magnetic field, an external magnetic field, because there is an internally generated magnetic field. Now, how do I find the regime of temperatures in which there is a non-zero magnetization versus the regime where the magnetization is 0, the sample is 0? Yes?
Wouldn't there be an infinite number of lines?
Yes, there would be an infinite number of lines. Fine. But how do I find the critical transition in the temperature? Remember that these are two phases of the material. One phase is that in a certain temperature regime, you have the sample magnetized spontaneously, even in the absence of an external field. And in the other regime, which is at a higher temperature, the sample is unmagnetized. The internal molecular field cannot magnetize the sample. And this becomes a temperature dependent phenomenon, and it happens at a precise temperature. So this admits of a phase transition. There is a certain temperature regime. This is my temperature. There is certain critical temperature, which is generally called the Curie point. Below this temperature, m can be non-zero, even when B equals 0. Above this temperature, m is always 0 when B equals 0. Now, how do I find this critical temperature from this graph?
Slope of the yellow graph.
The slope of the yellow at what point? At the origin. I find the slope of this yellow graph of the Brillouin function at this point, and I compare it with the slope of the green lines. When the slope of the green line is larger than the slope, this blue line, which is the slope of the Brillouin function at point 0, then I have this regime. Otherwise, I have this regime. So what I could do, I could actually find out this critical temperature. Let's find this out. Okay. Now, BJY, we all know, when y is small, of course y is small here. This is approximated as, let's find out what the series expansion of the Brillouin function is. We've already looked at that, but let's do it again. So first of all, I'm going to define the Brillouin function. So done over here. Alright, so this is my Brillouin function. It takes some value j, which is the angular momentum quantum number, function of y. This is how it is defined. This is what I wrote on the blackboard. This is my function. Now, I take, for example, a spin half particle. I can plot this. Let's first plot this Brillouin function. I plot this function as a function of y from, say, 0 to 8. Let's plot it from 0 to 5. Okay. So this is my Brillouin function. If I plot this from 0 to 3, this is what it is. This is the Brillouin function. Now the slope of this function at this point is what I need to determine. So I can differentiate all of this and put y equals to 0. Okay. The other thing that I could do, I could expand this function as a function of, as a series. So I take the series expansion of this, the variable is y, and I take the first two terms. So if you notice here, there is a term linear in y and a term y cube, y raised to power 5, and so on. Okay. So the lowest order term is just proportional to y. Okay. Now I can easily determine what the slope of this function is at y equals 0. So bjy at small y is y, and this is this thing over here. Okay. Now this, what I need to do, I need to find the slope of m. So I need to find dm by dy at y equals 0. Dy with respect to y. Right? So m equals ms, right? The zeroth order expansion is just equal to y, okay? So we know this, the lowest order expansion. Now from this equation, m equals ms bj of this. Now this thing is gj mu b let's call all of this, let's call this y. Okay, m equals ms into y. Now what is ms? ms is n times gj mu b j. This is the saturation magnetization, where n is the number of spins per unit volume, Gj mu b is the magnetic moment of each, into J is the magnetic moment of each spin. So this is M. Now what's the slope of this function? This is just the yellow line in the vicinity of y equals 0. Correct? Now the slope of this function with respect to y is simply given by n Gj mu b j, which turns out to be equal to ms. Alright. The slope of this equation is equal to this, which is the slope of the green line. So the critical point is reached when the slope of the green line equals this slope, which means that this term over here, Kb, T is some critical temperature now, over Gj mu b, the molecular field constant lambda J equals Ms, which means that my Tc equals Gj mu b lambda J Ms over Kb. Now Ms is also equal to n times Gj mu b Gj mu bj. So I get this. This is my Curie temperature. This is called the Curie temperature. At temperatures that are smaller than the Curie temperature, I get the green lines which make an intersection with the yellow line. And a non-zero magnetization can be sustained. There could be spontaneous magnetization inside the material. For T equals Tc, this only solution exists at m equals 0. Likewise for T greater than Tc. For T greater than Tc, there can be no non-zero magnetization that is sustained inside the material. So now this Curie temperature depends upon the saturation magnetization, and it depends upon this hypothetical constant lambda. Alright? Now if you notice this lambda ms is an internal magnetic field. Lambda times m is an internal magnetic field. So the Tc is equal to Gj mu b j, the internal molecular field Kb. Now there is some internal magnetic field which is being produced somehow. We have to explore the origins of this internal field. But that leads to a phase structure, which means there are certain temperature regimes in which non-zero magnetization or spontaneous magnetization can exist even in the absence of an external field. And if the temperature is beyond this Curie point, the internal magnetic field cannot create any magnetization. Now we need to explore the origins of this internal field. But first of all, let's look at what should be the magnitude of this field. How large should a field exist? For that, we need to know the Curie points. Now, it's good to remember the Curie points of a few materials. For example, iron has a Curie point of 1043 Kelvin Tc, right? Nickel has about 630 kelvins. This has about 1340 kelvins, about. Okay. So if iron is below 1043 Kelvin, it can sustain a spontaneous magnetization. So let's now plug in this value here for iron. Let's assume that for the time being, let's assume we just have For iron, in fact, this Gj, the the moment of each ion is about 2.2 mu b. Okay, this is something we know from experiments. So we put 2.2 mu b in place of this, in place of all of this. This is something we would like to calculate, and this is Kb. So BMF equals, an estimate of BMF is Kb Tc divided by 2.2 mu b. Now let's insert these values and see what kind of numerical estimate do we get for the internal field. So I have 1.38 into 10 raised to the power minus 23, which is my Boltzmann constant, into Tc 1043 divided by 2.2 into 9.27 into 10 raised to the power minus 24, which is the Bohr magneton. This is the field that I get. 700, about 700 Teslas. I can get a more accurate estimate if I use the proper values of J, etc. But this is the estimate of the field. Now, this field can never be generated through any wire which is carrying current or through a solenoid. This is a field that is impossible to achieve on Earth. Okay? You might have to go to a neutron star to get such a field. So, these large Curie temperatures are explainable by an internal molecular field, but that molecular field has to be explained somehow. Where is that molecular field coming from? Now, the point of the molecular field is that no such field exists in reality. There is no field in Tesla that exists inside the solid. What Weiss's theory, molecular field theory, says that if you would like to achieve ferromagnetic ordering of that kind, there has to be some mechanism to order the spins. Now, spins are ordered by magnetic fields. So there is an effective magnetic field that exists effectively inside the solid, which is of a large magnitude, about 1,000 Teslas, which is going to order those spins, which is going to put them in an ordered state. Now we have to look what is the origin of this molecular field. First of all, we've seen that an internal molecular field is capable of describing this biphasic behavior. That is, below a Curie point, you have a ferromagnetic material, and above the Curie point, this material transitions into a paramagnetic material. So this transition from a ferromagnetic material to a paramagnetic material happens at the Curie point. Remember, in the freshman lab, there is also an experiment that determines the Curie point. Alright, now let's look at the susceptibility. So we would now like, okay, before that, what we would like to do is, what I'm interested in doing is, I would like to make a plot between the magnetization and the temperature in the absence of a magnetic field. So remember, I have not yet switched on a magnetic field. Okay? For a paramagnetic material, I have T here, and if I were to plot the susceptibility, I know that the susceptibility follows the Curie law. Okay, it decays as 1 over T. So whenever we would like to do magnetization studies, we would like to see the temperature behavior of magnetization. So what we are interested in doing is, what is the magnetization versus temperature behavior of a ferromagnet? First of all, we would like to see the ferromagnetic state. If you are below this temperature, how does the magnetization change with temperature? So the answer to that question lies in in these equations, nothing else but these equations. Okay. So what we would like to do now is we would like to plot this graph. So in other words, what we would like to do is the following. आप कैमरे में देख रहे हैं, ठीक है? So what we would like to do is the following. We have y here and we have m here. One graph is for the Brillouin function. Okay. The other graph is the relationship between y and m. It's a straight line. Now this is a point of intersection. This is a graphical, this is the solution to both of these equations. And the solution, suppose, is y star. We would like to find out y star. And from the y star, we would like to find out what is the corresponding m at this y star. Now this y star is proportional to the temperature. So for each temperature, we can find the corresponding magnetization. And that's what we would like to do here. We would like to find the magnetization versus temperature, which means that we would like to solve both of these simultaneous equations, and that can be solved by looking at the intersection of the Brillouin function graph and the straight line. This will give us the solution. This will tell us what the temperature is, and at that temperature there is a corresponding magnetization, and then we will be able to make this plot over here. So what we would like to do is we would like to solve these equations right over here. So we would like to do the following. We would like to solve ms bj y equals y kb t over gj mu b lambda j. Correct? You like to solve this equation for y. You like to find out the y, the solution of this equation for different values of temperature, by the way. Okay? And then we would like to find the corresponding magnetization. So what we could simplify this a little bit in the following fashion. We know that we've already found out what Tc is. Tc is given by ms gj mu b lambda j over kb. So if we look here, kb gj mu b lambda j, all of this appears here. अच्छा ये एक मिनट. So this is BJJY. This is a plot. Now I would like to relax this requirement that we have a spin half. So if I have a spin J, okay, and if I just look at the first coefficient, it's the lowest order coefficient is 1 plus J this is ms 1 plus j over 3j y. So I want to relax the condition that I have a spin half particle. Okay? So if I relax this condition, all of this is going to change. The slope will be, now the slope will be ms into 1 plus j over 3j. Okay? So this is going to be the slope for an arbitrary j material. Okay? So this is the slope. Now I would like to make another correction here. ms 1 plus j over 3j. I would like to keep the j totally arbitrary. This means that my Tc is equal to Gj mu b lambda j ms over kb into 1 plus j over 3j. Okay? So there is a 1 plus j over 3j here as well. Sorry for that. This is for the general case. This is Tc will have a 1 plus j over 3j as well. This result could change. For example, if j equals say 1, j equals 1/2, I can change this. This will be of the same order of magnitude, okay? 1000 Teslas perhaps. Now what I would like to do, this is my Tc. Alright? Now I have to solve this equation. ms bjy equals this. I know that Tc equals this, 1 plus j over 3j. Now if I look at the terms over here, kb, gj, this object here is, I can write the following. Tc ms j 1 plus j 3j 1 plus j 3j msj equals gj mu b over kb. Now this thing can go in here, which means that my ms bjy equals y t. All of this is expressed in this form. Tc, now this j goes away. I have 3 here, ms 1 plus j. Now this is my equation. This y just goes, this ms just goes away. And what I have to do, I have to solve this equation. bjy equals t over tc 1 plus j over 3 into y. Is there another j that I am missing? Tc is this 1 plus j over 3j. So there is a j. Am I missing a j somewhere? ms bjy equals y kb dj mu j t. Now my Tc equals ms dj mu b lambda j kb 1 plus j over 3j, which means that my dj mu b lambda over kb Tc 3j ms j 1 plus j. Okay. Now there is this j here, kb, so I have a j here. Okay. So this is the equation that we need to solve. The solution to this equation will be my y star. And with respect to that y star, I can find out the magnetization. Okay, so let's solve this equation. Of course, I need to use a computer to solve this equation. I'll solve it graphically. Okay, so let's do this. Alright, first of all, if you observe, I look at this graph here, the Brillouin function graph, say I plot up to 5, and on top of this, what I would like to do, I would also like to plot this thing. Now this thing is going to be a straight line. So I can plot this, and I've already done that here. So I put in an angular momentum of 1/2 y 1 plus j over 3j 0.5 into y. Alright, so what I've done over here, this is a plot of the Brillouin function for a spin half particle, and this is the right hand side of this equation. Look, I have a y, I have a 1 plus j over 3j into T over Tc. So my temperature is 1/2 the Curie point. If my Curie point is 1000 Kelvin, this is a graph at 500 Kelvin. I am below the Curie point, which means there is a point of intersection which corresponds to a non-zero y and a non-zero magnetization. I can change this temperature. This is my temperature variable. I can change this. For example, if I go to even lower temperatures, look at this graph. I'm going to lower temperatures now. See, instead of 0.5, I plot 0.3. I will get a line which has a shallower slope, which means I'm at lower temperatures. Now, at this lower temperature, my y is higher. My y is higher, and I have to find out what my magnetization is. The magnetization is going to be slightly higher than the magnetization here, but it's going to be roughly the same as the magnetization here. So lowering the temperature further does not change my result. Okay? So this magnetization is almost the same as this magnetization. So this graph over here is going to be a non-linear graph. If I increase the temperature a little bit, so I increase the temperature, and here I'm going to do that. So I go to 0.8, 80% of the Curie point. Now at 80% of the Curie point, I get this graph over here. So this corresponds to some y, and it corresponds to some magnetization, which is lower than the magnetization here. So as the temperature goes up, the magnetization drops, which is expected for a magnetic material. If I take the Curie point, I will see that the line that I'm going to draw is going to be tangential to this Brillouin function, and I'm going to make a phase transition. So if I make the temperature equal to the Curie point, you will notice that I will make a green line that is tangential to the Brillouin function equation. If I go 50% beyond the Curie point, there is no intersection between the two equations, which means I will only get a zero magnetization. There is no spontaneous magnetization that can be sustained at zero fields. Okay, so now I would like to find out the solutions to both of these equations, which means what I'm going to do here is exactly the same thing. I'm going to assume that I have a spin half system. So I put j equals 1/2, and I'm going to look at the Brillouin function, and I'm going to equate it to this factor over here. Now the beauty of this is that I have a temperature which is a ratio of the Curie point, so I don't need to put in precise, I don't need to know the Curie point of the substance. Okay? So this is just a ratio. So I'm finding y as a function of T over Tc, which is the ratio of the Curie point. So this is the right hand side, y 1 plus j over 3j, and This is the ratio T over Tc, K, and I'm varying K from 0.01, which is very low temperatures, to the Curie point itself. This K equals 1 corresponds to the Curie point itself. So I'm varying K and I'm finding the solutions to this equation numerically. That's what I do here. So what I'm going to do, I'm going to take this to the other. So I find the solution. These are my solutions. These are the values of y's that I get. For 1% of the Curie point, my y is 100. For 0.2% of the Curie point, my y is 50, and so on. You will observe that as my temperature is increasing on this axis, the y is coming down and down and down. Now, corresponding to that value of y, which is coming down and down and down, I have to find out the magnetizations. So how do I do that? I just insert these values of y into the Brillouin function. So I'm going to do that now. I have Bj, it's a spin half system. I have my values, my solutions, which I call Z1, and I'm going to plot this. Let's list plot this is my solution. I'm going to do list line plot. Now what is this axis is my T over Tc axis. This 100 means 100%. So this is my Curie point. At my Curie point, the magnetization has dropped to 0. At 0 temperature, the magnetization is equal to ms. This graph is, see, this is my equation. This graph, the solution to this equation is, this is the Brillouin function into ms. So this is ms over here. And as the temperature increases, my magnetization drops. This is a characteristic curve for how the magnetization of a ferromagnetic material changes with temperature. But here I have assumed that I have a spin half system. Let's assume that I have a spin, say, 1 system, an angular momentum 1 system. So I repeat this calculation for a spin 1 system. We call it solution 2. Suppose I have spin 1 system. So spin 1 Z2. I get this magenta curve, this curve over here. Alright, so by changing the spin, by increasing, this is for a spin half system, this is for a spin 1 system, I can draw graphs of spin 3/2 systems for arbitrarily large angular momentums. Let's do a spin 1000 system, which is like classical magnetic moment. So infinities disturbs this mathematical a little bit, so I'm using a large value of j, which is 1000. G. Alright, so I get this graph. So for infinitely large quantum numbers, which are classical magnetic moments, I get a curve that is similar, and all the values of J will lie in between in this regime. For 3D elements, it's easy. My J is equal to the S, so I can just look at the spin of the ion because the orbital angular momentum is quenched. For 4F ions, however, I have to take the overall J. But this is the general behavior. The magnetization drops as the temperature goes up, and there's a phase transition here at which the magnetization goes to 0. Now the magnetization of a paramagnet beyond the Curie point is a minuscule of the magnetization of the ferromagnet, so it can be taken to be 0 on this scale. Now the last thing I would like to do before we finish this class is I would like to find out the susceptibility for a ferromagnet. Now the susceptibility is quite easy. I mean, the Curie point is a characteristic. What does the Curie point depend upon? It depends upon Ms, the saturation magnetization, which depends upon the number of spins per unit volume. It depends upon these quantities. So it's a macroscopic property. It's like a critical temperature at which a phase transition occurs. So it's for all spins inside that material. No, the Curie point is a constant. This is the temperature axis. In this temperature axis, this is the Curie point. This is 80% of the Curie point. This is 60% of the Curie point, and so on. This temperature is written in a ratiometric, in a dimensionless form. It's a ratio of the Curie point. Okay. Now the last thing I would like to do, the last 2 minutes, is find out the susceptibility. But before that, I think it is a more interesting observation. Okay, we can actually do this in the next lecture because it's going to take some more time. So in the next lecture, what I would like to do is, what have we learned? First of all, we've learned that a ferromagnet is a magnetically ordered state. There is some internal magnetic field that is generated, which cannot be described by real fields. It's not a real field. There's no real fields are produced by wires which carry current. No such field exists. But effectively, there has to be some equivalent of this field which is ordering the magnetic material because the Curie point is so high. The Curie point is so high, the measure of the Curie point gives us the measure of the molecular field, and that molecular field turned out to be of the order of 1,000 Teslas. So this is a large field that effectively exists inside the solid. This amount of field is required to order the spins inside the domain. Now what we've done is we've looked at the temperature dependence of the magnetization. The general form is like this. This is M over Ms and this is T over Tc. Okay? The general form is like this. All of this is the ferromagnetic state. For temperatures higher than Tc, you have the paramagnetic state. So this is like a phase diagram in which below this curve you have the ferromagnetic phase, and beyond this curve you have the paramagnetic state. So it's like a phase diagram. So a phase transition occurs. And by the way, this is a magnetization curve. Magnetization we know equals minus the derivative of the free energy with respect to the magnetic field. Now the magnetization itself is continuous, but its slope is discontinuous. Look at the slope here. There's a sudden change in the slope. So dm over dt, dm over dt is discontinuous. So the second derivative of the free energy is discontinuous, which means this is a second order phase transition. Associated with this second order phase transition, there has to be a latent heat, and there has to be a thermal expansion associated with this second order phase transition. Okay, so you can do a specific heat measurement with respect to temperature to find out the phase transitions as well. You don't need to do a magnetization versus temperature measurement. So these properties are also revealed in the thermodynamical properties of this particular material. So we've noticed that there is a phase transition, there is an internal molecular field. In the next lecture, what we would like to do is we would like to generalize this a little bit. First of all, like to switch on a magnetic field. We switch on a magnetic field, you will notice that no phase transition can take place. Number two, we would like to find out the susceptibility. We would like to find out a similar graph for a ferromagnetic material. This is for a paramagnet. For a paramagnet, we know that the susceptibility is some Curie constant over the temperature. Higher the temperature, lower the susceptibility. A similar behavior is expected for a ferromagnet, but what is it precisely? What is the Curie law for a ferromagnet? Third thing, we would like to see how do we apply this scheme to an antiferromagnet. And what's the Néel temperature of an antiferromagnet? The next thing we would like to look at in the next lecture is what is the origin of this molecular field. Like to describe that the origin is in the exchange interaction. Okay? Thank you very much.